And does anyone know what else, what the story is if you start with these axioms? You will get the projective planes certainly match this over a field, the way that we introduce them. You will get weirdos. You'll get projective planes that cannot be written down as a vector space, three-dimensional, where you take the one- and two-dimensional subspaces. And the first one was found in 1905 by Moulton, an American mathematician. So the Moulton plane was the first. Actually, by the way, Hilbert in his book also had an example for a projective plane that satisfies these axioms, but it's not of the form that we started with, that we were expecting. Okay? So there was our first surprise. And ever since, and it's not finished, ever since mathematicians, geometers have tried to classify projective planes. They are not done. And they won't be done soon. So there is a remedy. So you just put in another axiom that gets rid of these exceptional examples. Does anyone know the axiom that is needed to eliminate these non-classical projective planes? It's one of these old incidence geometric theorems. There are two theorems around. One is the theorem of Pappus, and the other is the theorem of Desargues. I don't want to go into this because I don't want to spend all the time here in the lecture. If you have a time, Google Pappus and Google Desargues. The short answer is, in the finite world, if you put either Desargues or Pappus, now the theorem becomes an axiom. If you put the statement of the theorem, it's a theorem about the classical projective plane. If you generalize it to axiomatic projective planes like these, it becomes a statement. It may be true or not, may not be true. So you can use it as an axiom, and if you put this axiom, you eliminate all the non-classical projective planes, and the only one that survives is the projective plane over the field that we discussed. So you can sort of solve the whole thing. Okay? But that doesn't stop mathematicians from still asking the question, what kind of projective planes are there that just satisfy these 3 or 4 axioms? Okay, so, but this is just an example for this reverse engineering process. We start out with a set of axioms. We want to ask what kind of objects satisfy these axioms. And now I want to go to a second example. Now we want to reverse engineer the conics. So going back to the conics, and the defining property for us, it was just written down there. A conic, if you intersect it by a line, you hit at most 2 points. What if we would start from there? What if we took this as our axiom? And we would then say, well, we want as many points as possible. Does that make sense? Okay. So does that make sense? So we have seen the conic has the property. When you hit it by a line, you see 2 points at most. By the way, so let me just put this. You have either 2, 1, or 0, and you would call L is a secant in the first, a tangent, the second, an external line in the third case. We know about secants and tangents. Why do we talk about these external lines? We haven't seen them before. Well, actually, they also happen over the real line, so over the real plane. So we have these 3 possibilities coming from here. So what we want to do now is we want to build a new theory of conics. Maybe I shouldn't call them conics. So we want to ask the following axiom. So A, a subset in PG2Q. And we want to put that when you intersect it with a line, you hit at most 2 points. This is for all lines. And now the question is, I'm going to leave out the second axiom, which is about the size. I'm going to leave this out for a while, so I want to put this as a question. And this was a question that an Indian mathematician with the name Bose has asked himself, 1947. 1947, Bose asked this question: how large can A be? That's a pretty natural question. Yeah. Does anyone know the answer? It seems like we're going to get close to q plus 1. That's somehow the intuition from the conic. Okay. So, by the way, the degenerate conics don't show up because they don't satisfy this first one. So we got rid of the degenerate conics by putting the first axiom. Yeah, because they contain lines. Remember the picture? We have these 2 points on the projective line, and they kind of get extended up to infinity in the z direction. So, and there you see a line that intersects more than 2 points. So we got rid of those. So we're left with the conics. The conics are still good. And now Bose asked this question. Actually, Bose answered this question. Theorem, Bose, 1947. He wasn't supposed to be doing this. His boss at that time wanted him to work on statistics, but he just found this more interesting, and so in his off time, he proved this theorem. So he proved that, this is called an arc, by the way. Yeah, if we just leave out this, an arc is just this. And Bose proved that the size of an arc is at most q plus 2. And here's the proof. Let's say this is our arc. Now, in reality, it's just a bunch of points, yeah? Pick one point. Let's say, pick this guy. Yeah? Now, what do we know about projective planes? Any 2 points determine a line. So I know I have determined all these lines. Well, wait a moment. This looks like the pencil of lines. What do we know about the pencil of lines through a point? Well, we know that the size of the pencil is q plus 1. In other words, the number of lines here is bounded by q plus 1. Yeah, guess what? That means we have bounded the size of the arc by q plus 2. Easy. Make sense? We could have had this idea too. But no one asked us. Anyway, so now we want to focus on the large arcs. So we say that A is an oval if the size of A is q plus 1. And we say that A is a hyperoval if the size of A is q plus 2. It's conceivable, according to the bound, we could have q plus 2. It's not going to be a conic. Yeah? It's a combinatorial object that behaves like a conic in a certain sense. It can't be a conic. And so how did the story go on? Well, right now we're a little bit confused because we have weird things coming up. The bound doesn't match the experience. The bound here, q plus 2, doesn't match our experience from the conics. And so, well, we're confused. So we're asking the question, let's say if we focus on this case, which is clearly the one where the conics would be, we ask the following question. Is every oval a conic?